Che dici? Beh, vabbè.
Hai cominciato?
Okay, so you see my screen because I did not check the rest?
Yes, yes, we see it.
Yeah.
Yes.
Okay. Okay, so after a few lectures of discussing complex Monge-Ampère equations and pluripotential theory, I'm now going back to the original geometric motivation, which is the construction of canonical metrics. And today we are going to do two things. So I'm going to recall the definition of some canonical scalar metrics, present a few methods to construct them, and I will also discuss, so that the first lecture will be a bit panoramic, and in the second lecture I will focus on the most difficult case, which is the case of positive curvature and with mild singularities. Okay, so but first maybe let me recall the few definitions we have passed in the first lecture. So X omega is a compact scalar manifold of complex dimension n, as always, I would say. And locally, you can write such a form omega in local coordinate like this. And then its Ricci curvature form, this is something I explained in the first lecture, is essentially minus the curvature of the log of the determinant of this scalar form omega. And although this is a local expression, I recalled in the first lecture that this reach of omega defines is well-defined, globally well-defined one-one form, which represents the first Chern class of X. Okay, and an important historical question is that conversely, if you give yourself eta, which is a closed differential form representing the first Chern class, can you find a scalar form omega whose Ricci form is exactly equal to this eta? So in one direction, this is something I said in the first lecture. If you pick omega, then Ricci omega represents C1 of X. And then Calabi in the 50s asked about the converse. And this problem remains open for a few decades, and it has become known as the Calabi conjecture, a very famous conjecture in the field. And it was solved by Yao in the late 70s as a consequence of the resolution of complex Monge-Ampère equation. So what Calabi explains is that in order to resolve this question, one would be led to solve a complex Monge-Ampère equation as follows. Namely, if you fix alpha, a scalar cohomology class, if you pick omega, a scalar form representing alpha, then by the Didi-Bar lemma, if you fix eta in C1 of X, then eta and reach of omega are DDC cohomologous. So you can find H, a smooth function, so that reach of omega is equal to eta plus DDC of H. And of course, the Calabi problem would be solved if you can somehow reduce to a situation where H is zero, or let's say H is constant. So the way to try and do this is that you perturb omega by adding DDC of a smooth function of a scalar potential. So we seek for not omega, but omega phi, which is omega plus DDC phi, such that reach of omega phi is equal to eta. So if you write down what it means, well, eta should be reach of omega phi, but reach of omega phi we know is globally equal to reach of omega minus DDC of the log of the ratio of the volume of the scalar forms. And on the other hand, we know that reach of omega is eta plus DDC H. So what you get is that eta is equal to eta plus DDC of H minus the logarithm of the ratio of the volume. So the etas cancel out, and what you get is that DDC of the function which is inside the bracket should be zero, but we are working on a compact manifold. So there can be no pluriharmonic function but the constant. So this function inside the bracket should be constant. And therefore, what you end up with is the following complex Monge-Ampère equation if you raise to the exponential, if you compose by the exponential function, namely omega phi to the n is equal to e to the h plus some normalizing constant times omega to the n. So this is one direction which says that if we want to find omega phi so that Ricci of omega phi is zeta, then phi has to be a solution of this complex Monge-Ampère equation. And the reverse is also true and even simpler. So if phi is a solution of this Monge-Ampère equation, then Ricci of omega phi is equal to eta. So solving the Calabi problem is equivalent to solving this complex Monge-Ampère equation. And this is exactly what Yao did. So let's normalize, so let's fix the value of this unknown constant here. And this you can do by normalizing h so that the mean value of h is equal to the mean value or is equal to 1. And then what Yao proved is that this complex Monge-Ampère equation, once h is properly normalized, admits a smooth solution. So phi is a Kähler potential, which is smooth. And this solution is unique up to an additive constant. So this you already know because we have explained the proof, or not all the steps, of course, but at least the strategy and one of the main steps of the proof within lecture 4. So we can smoothly deform the equation to a known solution and prove a priori estimates in order to solve this result of Yao, to prove this result of Yao. So that was explained in lecture 4. And that's the first connection, strong connection between complex Monge-Ampère equations and finding spatial Kähler metrics. So resolving the Calabi conjecture. So here comes another important connection, which is through the notion of Kähler-Einstein metric. So a Kähler metric omega is Kähler-Einstein if there exists some real number lambda such that the Ricci form of omega is lambda times omega, so proportional to omega. This is a definition I gave in the first lecture, but in the middle of so many definitions and maybe you have missed it. And I already said that because reach of omega represent the first Chern class, there is an obvious homological condition for such a metric to exist. It is that P1 of X should have a sign. And although in dimension 1, this is always the case, so you know that compact Riemann surfaces are either P1 and then C1 of X is positive, or an elliptic curve, then C1 of X is 0, or a compact Riemann surface of hyperbolic type, and then C1 of X is negative. So that's for dimension 1, fair enough. But starting dimension 2, this is no longer the case. If you take simply a product of compact Riemann surfaces, then C1 of X has a sign if and only if S1 and S2 have the same type. So both P1s or both elliptic curves or both of hyperbolic type. So beware of that. Then another remark I made in the first lecture is that the Ricci form of a positive constant time omega is the same as the Ricci form of omega. So actually this Kähler-Einstein problem can be rescaled and reduces to treat 3 different cases, either lambda is -1 or 0 or +1. Now comes a slightly more involved definition. I won't say much about it, but it's important that you know it exists at least. In the case, say, when lambda is 1, I will explain briefly that they do not always exist Kähler-Einstein metric, but from time to time there exists closely related objects that are called Kähler-Ricci solitons. So a Kähler-Ricci soliton is a pair of a Kähler metric omega and a holomorphic vector field V on X, such that the Ricci form of omega is almost equal to omega, modulo an additive term, which is the Lie derivative of omega with respect to the holomorphic vector field. And these objects are very important in many respects, and kind of canonical Kähler metric as well, as you will see. Okay. What about the way of relating Kähler-Einstein metrics to complex Monge-Ampère equations? Well, here it goes. I fix this proportionality factor lambda, so that lambda omega is C1 of x. And as I said, Ricci of omega represents C1 of x. So Ricci of omega is cohomologous to lambda omega. That means again that there is a smooth function h by the Didi-Bar lemma, so that Ricci of omega is lambda omega plus ddch. And if we want to construct a Kähler-Einstein metric, somehow we want to kill this factor h. So once again, we seek for a perturbation of omega. So we look for omega phi, which is omega plus ddc phi. And we would like this omega phi to solve the equation Ricci of omega phi equals lambda omega phi. So with the same reasoning as previously, if you plug in this global relation between Ricci of omega phi and Ricci of omega, what you end up with is that the Kähler-Einstein equation, Ricci of omega phi equals lambda omega phi, is equivalent to the fact that ddc of h minus lambda phi minus log of the ratio of the volume is equal to 0. And once again, because x is compact, by the maximum principle, the function inside the bracket has to be constant. And therefore, the Kähler-Einstein equation is equivalent to solving the following complex Monge-Ampère equation. Monge-Ampère of phi equals e to the minus lambda phi plus h omega to the n. So what about the resolution of such equations? Well, of course, this family of equations for lambda equals 0 contains the Calabi problem as a particular case, but it's much more general. And here are the three main types of results depending on the sign of lambda. So, as I said, you can rescale and reduce to treat either lambda is -1, or lambda is 0, or lambda is +1. And the difficulty goes increasingly. So the easiest case is when lambda is -1. And then the statement regarding Monge-Ampère equation is that the corresponding Monge-Ampère equation, omega phi to the n is e to the phi plus h omega to the n, always admits a unique smooth solution, which is a Kähler potential. And therefore, there exists a unique Kähler-Einstein metric in negative curvature. So when C1 of x is negative, or if you prefer, from perhaps a more algebraic point of view, when the canonical bundle is ample. For lambda equals 0, we have already given the solution, but the connection is like this. If X is a compact Kähler variety whose canonical bundle is numerically 0, then in each Kähler cohomology class, you can find a unique Ricci-Flight Kähler-Einstein metric by resolving the corresponding complex Monge-Ampère equation. And then there is a jump in time in order to treat the case where lambda is +1. And we have had to wait for almost 40 years for this problem to be somehow resolved. And this is the following result by many authors, but with the main last contribution by Chen Donaldson. So if X is compact Kähler with C1 of X positive, then the following are equivalent. So first, you can solve the complex Monge-Ampère equation with the lambda equals +1. Second, so let me, I on purpose, only mention a slightly simplified version of the general result. So there is the unique solution to the complex Monge-Ampère equation, if and only if there exists a unique Kähler-Einstein metric, if and only if the some algebraic stability condition is satisfied, namely that X polarized with the anti-canonical bundle is uniformly k-stable. So I'm not going to explain what this means, this last condition, But this is the flavor that you should keep in mind is that you have a unique solution to a highly linear analytic transcendental PDE if and only if some very algebraic condition is satisfied for this Fano variety, Fano manifold. Rather than trying to explain this, which would take very many hours, let me give a few examples in the Fano case, which is the most difficult. So let's start with dimension 2. In dimension 1, there is not much to be said. The only Fano Riemann surface, compact Riemann surface, is P1, and then everything is clear. So in dimension 2, you don't have so many Fano surfaces, so it's either P1 cross P1 or P2 blown up at R points in general position with R being in between 0 and 8. So you can blow up to 8 points in general position, and then you get a so-called del pezzo surface, which is a Fano manifold of complex dimension 2. And in that case, the answer to this existence of Keller-Einstein metric is known from since 30 years. It goes back to a result of Tian in 1990. All these del pezzo surfaces do admit a Keller-Einstein metric, except X1 and X2. So if you blow up P2 at 1 point, or if you blow up P2 at 2 points, then such object, such Fano surface does not admit a Keller-Einstein metric. On the other hand, it turns out that X1 and X2 are toric surface. So for toric manifolds, I very briefly discussed toric objects last Tuesday. These are compact scalar manifolds with lots of symmetries, which are equivariant compactification of C star to the n. So it's easier to understand what happens with all these symmetries. And there is a beautiful result of Wang and Zhu from almost 20 years ago, which says that a toric Fano manifold admits a Keller-Einstein metric if and only if conveniently normalized, its barycenter lies at the origin. And one extra piece of information is that even if the barycenter does not lie at the origin, any toric Fano manifold admits a unique Keller-Ritchie soliton. So with all these symmetries, maybe you won't get a Keller-Einstein metric, but at least you will get an important object, which is a Keller-Ritchie soliton. And this is exactly what happens for X1 and X2. They do not admit Keller-Einstein metrics, they do not satisfy this barycenter condition, but they do admit Keller-Ritchie soliton, which is a very important object anyhow. And somehow, in the same spirit, I would like to advertise the following result by Thibaut Delcroix, who has, so Fano manifolds are very well studied objects with lots of symmetries. And it's very important to have in your handbags different type of construction with lots of symmetries. And Delcroix has developed a very interesting direction of research considering more general compactification. So rather than compactifying C star to the n, you can try and compactify other groups, other algebraic groups. So he has looked at equivariant compactification of some reductive groups, and he has developed, it has the same flavor as for Keller, for toric geometry. So you can read, because you have lots of symmetries, because it's a group action that is compactified, you have lots of symmetries, and you can transform the complex Monge-Ampère equation into a real Monge-Ampère type problem. And so you have Delcroix has developed a similar dictionary than the one for toric geometry in these cases, more general cases of group actions. And this has had important consequences recently in Keller geometry. So I'm not going to explain it, but I wanted to advertise it. Okay, now I took a jump in difficulties. So far, we were working with smooth manifolds. And it turns out that we need to allow to work on mildly singular varieties. So let me say a few words about that. The so-called minimal model program aims at trying to classify complex algebraic varieties in any dimension. And it turns out that in dimension 1, things are very well understood since the 19th century. In dimension 2, so the classification of algebraic surfaces, it has been understood thanks to the work of the Italian school from the late 19th century, early 20th century, and then the Japanese and the Russian school in the mid 20th century. So a long time ago. But starting dimension 3, life becomes incredibly more complicated. And in particular, it has been realized long ago that it's a necessity to accept to work with mildly singular varieties. So the plan for the next few slides is to explain what type of singularities we need to consider, what it means to be a Kähler-Einstein metric in that setting, how one can again translate this Kähler-Einstein problem into Monge-Ampère equation, which will become more degenerate, so degenerate complex Monge-Ampère equations, and explain how to solve them. Okay, so first, let me discuss the type of singularities. So the most important notion is that of log terminal singularities. Let me explain the definition briefly. So we are going to work with varieties that are normal. So in particular, there is a singular set, but this that I denote by X sing, and this singular set is a complex variety of complex dimension, of complex codimension greater or equal than 2. Then a manifold, it's a ugly definition, but it's important, a variety is called Q-Gorenstein if its canonical divisor exists as a Q line bundle. So one says actually that X is Gorenstein if the canonical divisor can be realized as a holomorphic line bundle, and it's Q Gorenstein if it's true up to the multiplication by an integer. So Q line bundle means that maybe Kx is not a holomorphic line bundle, but maybe a multiple of Kx would be a holomorphic line bundle. So now, a famous, important, and difficult result of Fibonacci, you can always resolve the singularities. So if you take pi, which is log resolution of the singularities of X, you end up with an exceptional divisor that lies above the singularities, which you can assume has simple normal crossings. And then when you pull back this Q line bundle, what you get is a classical adjunction type formula for the canonical bundle of the smooth object that resolve the singularities of X. And this will be a formula like this. And it turns out that the multiplicities AI play a very important role. They are called the discrepancies. And by definition, one says that X has log terminal singularities if it is Q-Gorenstein on one hand, and these discrepancies are always strictly bigger than -1. And one says that the singularities are canonical if actually the AIs are non-negative. And this definition is, of course, or hopefully independent of the choice of log resolution. And maybe I leave as an exercise that if you start from something which is already smooth and you start to blow up, so to make this operation, so I did not say that log resolutions are obtained by actually blowing up things, blowing up the singularities. If you blow up something which is already smooth, what you will see is that you get AIs that are actually positive, non-negative. So somehow, if you the things you should realize is that if you blow up very bad singularities, that you can get AIs which are very negative. And it turns out that these sets of singularities, so when AI is greater or equal than 0, this is a class of singularities which is stable on the blow up. So if you go on blowing up, then you will keep this condition satisfied. And the same for AI bigger than -1. Okay, so this is just what I said. And here are a few explicit examples by now. So this was the formal definition, which is a bit abrupt and difficult to digest. But here are a few simple examples. So let's first look at the case of dimension 2. So I take S, a normal algebraic surface. Then the following are equivalent. So first, S has canonical singularities. Secondly, S is locally isomorphic to a quotient C2 by G, where G is a finite subgroup of SL2C. So this is the precise local understanding of canonical singularities in complex dimension 2. And for log-terminal singularities, you have a similar characterization, but here you are looking at quotients where G is a finite subgroup of GL2C rather than SL2C. So it's a bit more large as a type of singularity. Another explicit example, well, first, if you raise the dimension, then quotient singularities are still log terminals, but the new and somehow very difficult thing for the analysis is that it's no longer the case that you deal with quotient singularities in general in higher dimension. So let's look at the following classical construction. You take a smooth degree D hypersurface of CPn plus 1. And you look now at the cone over H. So you look at, in Cn plus 1, you look at the cone over this algebraic smooth degree D hypersurface. Then you have a singularity at the vertex. The origin is a singularity of the cone. And this singularity is canonical if and only if D does not exceed n plus 1. Probably it's a useful exercise that you try and check this. And in particular, what I would like to stress is first that if you are not, if you don't feel comfortable with these definitions, and I would perfectly understand it is the case, keep in mind that perhaps the most fundamental type of example are the so-called ordinary double points. So you take the local model is like this. You take sum of the coordinate square equal to 0 in any dimension. This is a canonical singularity. But starting dimension 3, this is no longer a quotient singularity. You see, from the analytic point of view, if a singularity is a quotient singularity, well, you can try and resolve and make the analysis by working in the Euclidean setting with a G invariant construction. So this gives some way of trying to do the analysis. But if the singularity is not a quotient, then where can one start? So it's much more difficult. Okay, this was for example. And let me go on now with an interesting analytic point of view on the very same definition of log-terminal singularities. So let's take X, which is a Q-Gorenstein. So RKX is a line bundle. I choose a non-zero local section, holomorphic section, sigma. And then I consider the following construction. So I take sigma wedge sigma bar. So sigma is a N0 form. So sigma wedge sigma bar is almost a volume form, if you like. You multiply by the right power of square root of -1. And then you should raise to the power 1 divided by R because you're working with RKX rather than with KX. So this is a smooth positive volume form near in the small open set that you're considering on the regular point of the manifold, of the variety. And then we made the following observation some almost 15 years ago with Philippe Sidieux and Ahmed Zahiri. if you pick local equations, local defining equation for EI in a small neighborhood, then when you resolve the singularity of of this measure mu sigma, it will look like this. It's a product of ZI to the power 2AI times a smooth volume form on this small neighborhood of the smooth resolution. And therefore, this Kuber-Einstein variety has log-terminal singularities, which means that AI is strictly bigger than -1 if and only if this measure has locally finite mass near the singularities. So perhaps if you're more an analytic guy, then perhaps that's the good way to think about this type of singularity. It means that the canonical volume forms of the underlying singular variety have locally finite mass near the singularities, and this is if and only if the singularities are those so-called log terminal singularities. So this local construction of mu sigma can be globalized as follows. You pick a smooth metric of the canonical bundle, and then you consider, you slightly rescale the construction above. So you consider again sigma bar with I to the right power, but then you divide by the norm of sigma with respect to R phi. You raise again to the power 1 divided by R. And then what you can easily realize is that this mu phi depends on the choice of smooth metric, but turns out now to be independent on the choice of the local holomorphic non-zero section of Rkx. So you get a smooth positive volume form that way on the regular part of X. And once again, by the same lemma, it has locally finite mass if and only if X has log terminal singularities. So this is the analytic counterpart of the log terminal singularity problem. So let me now explain an important construction in algebraic, which is the so-called canonical model. So let's assume that X is a complex, compact scalar manifold of general type. That is to say that the canonical bundle is big, and from the algebraic point of view, what it means to be big is that if you look at the canonical sections, then as the power of kx you're considering raises goes to plus infinity, there are more and more pre-canonical holomorphic sections, global ones, and so many that you can birationally embed X into some large complex projective space. In a certain sense, this is the appropriate higher dimensional analog of compact hyperbolic Riemann surfaces. And here is a extremely important result by algebraic geometers. So Birka, who got the Fields Medal not long ago, Cascini, Aiken, and Markkanen obtained a bit more than 10 years ago the following important result. The canonical ring, so if you look at the set of holomorphic sections of any powers of the canonical ring, and if you look at the summation of this ring, then you obtain a ring which is finitely generated. And a simple consequence of that is that if you look at the so-called proj of this ring, then this object turns out to be an algebraic variety of some Pn, and it has only canonical singularities. And actually, it was known much before their contribution that if you know that it is finitely, the canonical ring is finitely generated, then this canonical model will have only canonical singularities, and that was the reason for these singularities to be so-called. And moreover, so you have X, you establish that this ring is finitely generated. That's the important contribution of these 4 authors. And then you, as a consequence, you get that the canonical model is a reasonably nice variety with mild singularities, canonical, and on that canonical model, the canonical line bundle is a non-holomorphic line bundle. So one way to summarize this is that if you start from a manifold of general type, then this manifold is smooth, but the canonical bundle is not ample. It is lacking some part of positivity. You replace X by something which is singular, X can, mildly singular. The 2 objects are birationally equivalent, X and X can. But what you gain, so you lose because you're introducing singularities, but what you gain is that the new canonical bundle on this new birational model is ample, so has the right positivity property. So in view of that kind of result, it is very natural to wonder whether one can generalize the Urban-Yau theorem. So does there exist an analogous unique Kalan-Stein metric of negative Ricci curvature, perhaps on the regular part of this canonical model, or not? So this requires one to define the notion of Kalan-Stein metric in this mildly singular setting. So this is what I'm going to do next. So I pick X. Again, I assume it is Q-Bernstein. I pick a Kähler form on X. And then I define the Ricci curvature in a slightly different way than what I did in the smooth setting, but which is equivalent. So I pick H, a smooth metric of Kx with weight phi, and I give as a definition that the Ricci form of omega x is minus the DC phi. And I want to do that in such a way that the new phi measure, so the smooth volume form that I described earlier, is exactly the nth power of omega x. So I can clearly always achieve that. And I leave as an exercise that this is actually equivalent to the previous formulation when x is smooth. And then once you have defined the Ricci curvature, well, we call omega x a singular Kalan-Stein metric if Ricci of omega x is proportional to omega x. So it's the same definition. Okay? Like in the smooth case, this Ricci of omega will represent the first Chern class of this mildly singular variety. So this for singular Kalan-Stein metric to exist, C1 of x again has to have a sign. Okay, so what is known in this singular context? So let's start again with the easiest case of negative curvature. So it's a result that goes back actually to contribution by Tsuji in the 80s, Sugiyama in the early 90s, and then by Essidieu, Zarier, and myself. So let X be a projective variety with log terminal singularities and assume that Kx is ample. So if you like, X is the X can from previous slides. Oops. Then there exists a unique Kalan-Stein current, which is a nice Horner's Kalan-Stein metric on the regular part. And globally, it has bounded potentials as you approach the singularities. So, okay, let me go on. Now, in the zero Ricci curvature case, if X is a compact Kähler variety with log terminal singularity, so no projectivity assumption, and Kx is 0, then same result as for Yau. In each Kähler cohomology class, you can find unique Ricci flat Kalan-Stein current. So again, meaning a smooth Kähler form on the regular part, which is a Ricci, whose Ricci curvature is 0, and which has globally bounded potentials as you approach the singularities. And much more recently, due to the contribution of very many authors. So let me just mention two very recent contributions. The same result. So I did not mention, but in the smooth case, this theorem that I mentioned that was solved by Chen Donaldson was called previously the Yao-Tian-Donaldson conjecture. And then it turns out that the Yao-Tian-Donaldson conjecture holds for this in this Q for Q Fano varieties. Okay, so in this context of singular Fano varieties. Okay, let me mention, because I realized that probably I forgot to emphasize that in the next slides, that a very important issue, which is not resolved as today, is to understand precisely the asymptotic behavior of this singular Kahr-Einstein metric as you approach the singularities. And it is pretty well understand when the singularities are quotient singularities, and except in one particular case that has been treated by Hein and Son a few years ago, this problem is essentially widely open. Okay, so what's, again, the connection between this construction of singular Kahr-Einstein metric and complex Monge-Ampère equations? So the method is very similar, and you can realize and you can show that resolving the Kahr-Einstein equation in this singular setting is equivalent to solving a complex Monge-Ampère equation. But what you do now is that you replace this smooth volume form, you need to replace it by this canonical volume form mu phi, whose construction I explained in the previous slides. And then, of course, if you want to do analysis, you perhaps feel more comfortable on a smooth, to work on a smooth manifold. So you use a desingularization. And then you pull back this complex Monge-Ampère equation to the desingularization. So what you end up with is a complex Monge-Ampère equation of the following form, where omega is the pullback by this desingularization, by this log resolution of omega x. So beware that omega is no longer Keller. It is semi-positive, strictly positive above the regular part of x, but only semi-positive above the singularities of x. And it is big in this context. Let's say it means that the total volume is strictly positive. Moreover, when you pull back this canonical measure mu phi, what you end up with, and this is something I already explained on the in a previous lemma, you end up with f dv, where f is the density which belongs to LP, which is smooth and strictly positive above the regular point of x, but above the singularities, you have simply a density which is in LP for some p strictly bigger than 1. And you have both zeros and or poles depending on the type of singularity that you're considering. For instance, you only have zeros if you start with a variety which has only canonical singularities. But if you have log terminal singularities, you also can get poles for your density f. So therefore, these equations are degenerate in two ways. The right-hand side is much more degenerate than what we have seen previously, and the reference form is lacking some positivity. Or rather, I should say its cohomology class is lacking some positivity. Okay, but nevertheless, there are many ways by now, and you are aware of quite some of them, in order to resolve this Monge-Ampère equation. So here is some way to summarize this. So first method, you can try and perturb smoothly the equation and establish a priori estimate. So let me come back to the equation here. What you would do is that omega is almost scalar. So you add, if you replace omega by omega plus epsilon time a Keller form on x prime, then you get Keller approximation of omega. And then mu is nice on, say, a Zariski open set. So you can, it is FDV, say, you can use convolution, so replace F by F epsilon in order to get a smooth positive density that strongly somehow converges to the density F. You do that, you know that you have a smooth solution, maybe at least in the case of negative or zero curvature, and you try and establish a priori uniform a priori estimates along this approximation process, and it turns out that you can do that. And the method of proof that I explained in lecture 4 for the uniform a priori estimate applies exactly the same way to this setting. So that's one possibility. Another possibility that I described last Tuesday is to use variational methods. In lecture 6 on Tuesday, I explained the essence of the variational method, and I did not emphasize that, but I let you go back to your notes. It does not depend on the fact that the form, for instance, is scalar. It applies exactly the same way if the form is semi-positive and big. And it was working with rather degenerate objects, so functions in E1, and it does not matter if the right-hand side is only in LP. Or actually, I explained the proof with a measure on the right-hand side, which was of the type LP density times the volume form. So the variational method I explained applies here perfectly, and I will use that in a certain way in the next lecture. So you will see again the rational approach showing up. There is a third type of approach which I wanted to discuss in lecture 3, but I was lacking time, which is the method of envelopes, similar to a viscosity method. So let me skip that because I was lacking time. And next week, next Tuesday, I will explain a different parabolic approach to solving these Monge-Ampère equations by Kähler-Ricci flow techniques, and that will be the main topic of next Tuesday lecture. Okay, so this is it for this panorama, and let me give a few references to close this first lecture of this morning. So the contribution with Esidu and Zeriai was proposed in this paper. This is where we introduced the notion of singular canalization metric and resolve a certain number of cases. The celebrated Yao-Tian-Donaldson conjecture has been solved essentially by Chen Donaldson's son in a series of papers and published in 2015 that I was mentioning earlier. Then the variational approach that I discussed last Tuesday, this is one thing. Then the variational approach, has been pushed one step further in order to resolve the Yao-Tian-Donaldson conjecture with a variational approach, so with a very different approach than what Chen, Donaldson, and Son did. And this is a paper that should appear in the next volume of the Journal of the AMS. And finally, the method of Berman, Buxom, Jonsson was pushed one step further in order to treat the Yao-Tian-Donaldson conjecture for spatial Q Fano varieties. And this is a paper that should appear within this year in a communication on pure and applied math. So you can find these last two papers. You can find, of course, the version on the archive, but they will appear in the next few months. Okay, so this is it for the first lecture of this morning. Absolutely need a coffee. Perhaps it's the same for you. So I suggest